As we begin to think about using R for projects, it's important to know that we don't want to just dive in and start to try to create code. Just as if we were going to write an article, we would start with planning. What comes first? What comes next? What do we want to convey to our readers? What conclusions do we want our readers to take away? So metacoding is much the same way. It is planning to talk to R. The term metacoding refers to a system for preparing to code in a computer language, such as R, by constructing a relational outline of the major tasks to be completed, then transforming this to a finer grain outline and continuing to develop more and more detail until the coder is prepared to translate the outline elements into the computer language. The key concept here is that we start big and then we start to hone down until we get the level that we can actually develop the language. That's no different than if we're writing an article. We would start with something like an outline or a concept map or a flowchart, something to get down the ideas that we want to convey in a big format. We don't just sit down and start writing words. We need to know what it is we're going to do at each step. Metacoding is related to and loosely based on concepts such as mock-up, reverse engineering, wireframing, and vaporware development, which are all terms used in engineering and in computer science. But here I've adapted it for what we're going to do when we create R projects. The steps in metacoding begin with starting at the end. Again, no different than when we write. We want to understand what we want to convey before we start writing, what we want our outcome to be. We want to think about the takeaway message for our audience before we actually write a single word. When we start a project in R, we need to know what the end objective is. We list the final outcome elements, and I propose doing so in geometric figures called GROWs, which stands for a geometric representation of outcomes. That's it. We're just going to use the word GROW so we don't have to keep talking about geometric representations. We should include in our GROWs what kind of objects we're going to have, what kind of graphs we want to construct, what kind of analyses we want to do, and so forth. But we start at a meta level. We start at the end. We can draw relational arrows to indicate elements that must come before other elements. For each GROW, we can determine the outcome elements we need for that GROW and construct new GROWs with relational arrows. That is, we're now coming down to a little bit more finer tuning. And we repeat this process over and over until we're at a level where we're comfortable with coding, where for each GROW, we can envision what it is we're going to need to do when we write in R. So let's look at an example. In this project, we will simulate 3 experimental conditions, a placebo and 2 treatments, with 30 participants in each condition. The responses, that is, the outcome measures or scores in each condition, should be normally distributed with a common standard deviation of 20. The means are placebo 70, treatment A 75, treatment B 85. After we have created the data set, we want to construct side-by-side box plots, calculate 5-number summaries to accompany the box plots, and use one-factor ANOVA to determine if mean differences can be inferred to the population of interest. Let's begin at the end. What ultimately do we want to see? When we look at our R notebook, what is it we're hoping to see? We're hoping to see these side-by-side box plots for each of these three conditions, the 5-number summaries. We're hoping to see an ANOVA. So here's my first picture. I have data for 3 conditions. I already know that research data of this type are best stored as a data frame, so even though I'm at the beginning stage, I'm going to go ahead and indicate that I'm going to use a data frame object for storing the data for these 3 conditions. From these data, I'll be able to create side-by-side box plots. I'll be able to create 5-number summaries. I'll be able to create my analysis of variance. Now think about what the next steps are going to be, the next level down. Not next steps chronologically, I'm showing you the end right here, but what needs to come before this? We're going to need to generate that data, aren't we? The other thing I see here is that in order to do ANOVA, I'm going to have a linear model. So I now have moved to a new diagram in which I'm expanding to finer grain on the previous diagram. My data for 3 conditions as a data frame are going to have a categorical variable and a quantitative variable. The categorical variable will have 3 categories. The quantitative variable will have the scores. I also know that I have to define a linear model and then use that linear model with the data frame in order to get an ANOVA. All right, so far so good. What comes before this? Let's keep going backwards. Well, we're going to have to create those variables with 3 categories, right? And we're going to have to create those variables with scores. That's really what comes before this. So in order to create our variable with scores, we have to generate scores for the placebo condition, for treatment A, and for treatment B. Now, can we go back any further? Perhaps you're ready to start here, but I'm going to take us back one more step in which we actually envision how we're going to talk to R about these steps. So for generating the scores, we're going to use R norm. For creating the variable with those scores, we're going to concatenate across the scores. For creating the 3 categories, we're going to be able to repeat each one of our category levels for as many times as there are individuals within the condition, so we can use the rep function. We can put those all together with cbind as a data frame. We can define a linear model with LM. We can use boxplot for the box plots. We can have tapply and summary for our 5-number summaries. We can have ANOVA with ANOVA.